I will get the equation x into dt by dx plus t is equal to x square into y, that means x into t upon x cube plus x cube t cube, right? So this is our new format of equation. So now this implies x into dt by dx plus t is equal to x cube t upon x cube into bracket 1 plus t cube. So x cube cancel, so after all I will get x into dt by dx is equal to t upon 1 plus t cube. This plus t comes in this side, so this is minus t. So x into dt by dx is equal to t upon 1 plus t cube minus t. By simplifying this term, we will get x into dt by dx is equal to t minus t raised to 4 upon 1 plus t cube. So by simplifying this term, I will get x into dt by dx is equal to minus of t raised to 4 upon 1 plus t cube. And here the variables are separable because here all terms are with t. So I will get 1 plus t cube upon t raised to 4 into dt is equal to minus 1 upon x into dx. Here in the left hand side all terms are with t, and in the right hand side all terms are with x. So here this is 1 upon t raised to 4 plus this is 1 upon t into dt is equal to minus 1 upon x dx. And if I more simplify this term, then I will get here t raised to minus 4 plus 1 upon t into dt, that is equal to minus 1 upon x dx. Okay, so here variables are separable, so by integrating both sides, I will get integration of t raised to minus 4 into dt plus integration of 1 upon t dt is equal to minus integration of 1 upon x dx. So the final answer I will get t raised to minus 4 plus 1, that is minus 3 upon minus 3 plus log t is equal to minus log of x plus c. And if we put the value of t as a y by x in this term and here, then it will be our final solution of differential equation, which we can see in the PPT. Okay, here if I put t is equal to y by x, then I will get minus x cube upon 3y cube plus log y by x plus log x is equal to c, and the final solution is minus x cube upon 3y cube plus log y, because here log y upon x plus log x, that is equal to log y, is equal to c, which is our required solution, right? If we discuss about this example, we need to solve the differential equation x into dy minus y into dx is equal to in root x square plus y square into dx. So here we should note that here in the left hand side there is a term with dx and there is also a term with dx in the right hand side. So first we need to simplify that term. So we will get here x into dy is equal to, in bracket, y plus in root x square plus y square into dx, because y and in root x square plus y square both are the terms with dx. So if we put the dx common, then we will get x into dy is equal to, into bracket, y plus in root x square plus y square into dx. અને એ પછી જો આપણે ઇક્વેશનને રેગ્યુલર હોમોજીનિયસ ડિફરન્શિયલ ઇક્વેશનના ફોર્મેટમાં કન્વર્ટ કરીએ તો આવશે dy બાય dx ઇઝ ઇક્વલ ટુ y પ્લસ ઇન રૂટ એક્સ સ્ક્વેર પ્લસ વાય સ્ક્વેર અપોન એક્સ. જો આપણે y અપોન એક્સ ઇઝ ઇક્વલ ટુ ટી દરેક વખતે જો ઇક્વેશન હોમોજીનિયસ ડિફરન્શિયલ ઇક્વેશન હોય ત્યાં સોલ્યુશન માટેની ટેકનિક સેમ છે, એટલે કે આપણે y અપોન એક્સ બરાબર ટી લેશું. એનો મતલબ કે y ઇઝ ઇક્વલ ટુ xt લેશું, અને જો એનું ડિફરન્સિએશન કરીએ તો આવશે dy બાય dx ઇઝ ઇક્વલ ટુ x ઇન્ટુ dt બાય dx પ્લસ t. એન્ડ બાય પુટિંગ all these values in our main equation, we will get x into dt by dx plus t is equal to y plus in root x square plus y square upon x. Okay, and y upon x is equal to t, so I will put y is equal to xt. So I will get this kind of equation, and by simplifying, after all, we will get 1 upon in root 1 plus t square into dt is equal to integration 1 upon x into dx, and that is variable separable format. So by integrating both sides, we will get log integration of 1 upon in root 1 plus t square, that is equal to log t plus in root 1 plus t square is equal to log x plus log c. So our by replacing the value of t by y by x, so after all simplifying all these things, I will get the solution y plus in root x square plus y square is equal to x square c, which is our required solution. So in this way we can solve the homogeneous differential equation. Okay, now so we have already discussed how to solve the homogeneous differential equation. Now our idea is to solve the linear differential equation, which is our last method of solution to solve the differential equation. First we have discussed the variable separable method. Second, we have discussed the homogeneous, how to solve the homogeneous differential equation, and now our idea is that how to solve the linear differential equation. Before that, first we try to understand what is the meaning of linear differential equation, or what is the definition of linear differential equation. If we look at the PPT, then a differential equation is said to be linear if dependent variable and its derivative occurs only in the first degree and they should not be multiplied together. I have repeated the definition that a differential equation is said to be a linear differential equation if the dependent variable and its derivatives occurs only in the first degree and they should not be multiplied together. એનો મતલબ કે જે ઇક્વેશનની અંદર, જે ડિફરન્શિયલ ઇક્વેશનની અંદર ડિપેન્ડન્ટ વેરિયેબલ, નોર્મલી સ્પીકિંગ આપણે ઇન્ડિપેન્ડન્ટ વેરિયેબલ તરીકે એક્સ લઈ છીએ અને ડિપેન્ડન્ટ વેરિયેબલ તરીકે વાય લઈ છીએ નોર્મલી. તો ડિપેન્ડન્ટ વેરિયેબલ કે ફોર એક્ઝામ્પલ હું એમ કહું કે ડિપેન્ડન્ટ વેરિયેબલ that is equal to y, then y and its derivatives, that means dy by dx or d square y by dx square or d cube y by dx cube, all should occurs in the first degree. Okay, here we are discussing only for the first order and first degree of differential equation, so degrees must be first, and here we will take the linear differential equation of first order only. And secondly, they should not be multiplied together, that means y and dy by dx should not be multiplied together. Then and then this kind of differential equation is known as linear differential equation. The general form of linear differential equation of first order, because we are discussing here the differential equation of first order, then the general format is dy by dx plus py is equal to q. Note that here y and dy by dx, the degree of y and dy by dx is 1, which is the first condition for the any equation to be a linear, that dependent variable and its derivatives occurs only in the first degree. Here y there is a degree 1 and dy by dx there is a degree 1. So this is the satisfied first condition, that dependent variable and its derivatives occurs in the first degree and they should not be multiplied together, which is our second requirement. So here y and dy by dx, y and dy by dx is not in the multiplication. Okay, so the second condition is also fulfilled. So this is the linear differential equation of first order, right? So, and this is the general format of a linear differential equation. Note that here p and q both are functions of x or constant, but here there is not any terms of y in p and q. એટલે કે અહીંયા p અને q બંને x ના ફંક્શન હોવા જોઈએ અથવા તો કોન્સ્ટન્ટ હોવા જોઈએ. ત્યાં y વાળા કોઈ પણ પ્રકારના ટર્મ આવી શકે નહીં, because if there is any terms with y in p and q, then this equation will not be linear by the definition. Okay, so p and q both are functions of x or constant. This kind of equation is also known as Leibniz linear equation. Okay, this is the linear equation of first order. This is also known as Leibniz linear equation. So now our idea is clear that which kind of equation is known as linear differential equation. Now is our idea to solve the linear differential equation. We have some steps to solve the linear differential equation. This is the method for solution of linear differential equation. In first step, we will write the given equation in the standard form, in the general form of a linear differential equation, which is dy by dx plus py is equal to q. And in the second step, we will find the integrating factor, which is equal to e raised to integration p dx. Note that when we comparing the given equation with dy by dx plus py is equal to q, at that time we will get the value of p and value of q. Both are the functions of x, and then the integrating factor, that is equal to e raised to integration p dx. And in the third step, the general solution of this kind of linear differential equation is given by y into integrating factor, which we have find is equal to integration q, which is given into integrating factor dx plus c. So in this way we can solve the differential equation. Let us look at some examples of linear differential equation. Okay, so let us look at the question is solve the differential equation x into dy by dx, which is equal to x plus y. We want to solve this differential equation. First, we will check that whether the equation is linear or not. So here y which is dependent variable. So here y and dy by dx both are in the first degree and they are not in the multiplication. That means the given equation is linear differential equation. So now we will try to convert this equation in the general format. So I will take x into dy by dx minus y is equal to x. So if we dividing the equation by x, so we will get dy by dx minus 1 upon x into y, because I have divided by x here, so there is a 1, so 1 upon x into y is equal to x upon x, that is equal to 1. Okay, so if I write this equation again, so I can write here dy by dx plus minus 1 upon x into y is equal to 1, and this is linear equation in the general form, because if we compare this equation with the general equation, which is dy by dx plus py is equal to q, then here this is dy by dx plus py is equal to q. So we will get implies p is equal to minus 1 by x and q is equal to 1. So now we know that for the solution in the first step we will convert the given equation in the general format, and then comparing with the general format we will get the values of p and q. Then in the second step, step number 2 is to find integrating factor. Integrating factor is equal to e raised to integration p dx, right? So here p is equal to minus 1 upon